Hi everyone. In this video I am going to cover week 2 topic operating system software. So in this video we are going to completely discuss about memory management decisions. So the memory management portion of an OS depends upon the three fundamental areas of choice: whether or not to use virtual memory technique, the use of paging or segmentation, or both. The algorithm employed for various aspects of memory management. So these three are the fundamental areas by which the memory can be managed efficiently. So without the help of this virtual memory, paging, segmentation, and other policies associated with the memory, without that we will not able to, or the operating system not able to manage the memory efficiently. So before going into this, I just wanted to sort out there are few uh, concepts about virtual memory. So let's see this is secondary memory, and out of which we are going to reserve a portion, and which is going to be called as a virtual memory, and there will be a main memory, so where we are going to load all the process which we wanted to execute. So the operating system is interested in keeping all the process which needs to be executed in the main memory. So ultimately the operating system is going to bring the process and the programs which needs to be executed from the secondary memory to the main memory, right? Yes. So now say in main memory, if it is accommodated, that is completely it is occupied by the programs. Let's see, it can be occupied by the process whichever are being executed at this moment, and there are a lot of process which are blocked. So the blocked process are nothing but it is waiting for some event to occur. So I hope already we have discussed in the process states. So there we have discussed about 5 different states. Then we have discussed about suspended state too. So there I have explained you about what is virtual memory. So from blocked state into the process whichever are in the blocked state will be moved into the virtual memory, and there we are going to call the process whichever are going to be moved into virtual memory is called as a blocked suspended, because it is going to be reside in the secondary memory, but we will call it as a virtual memory. So the operating system is going to feel it like as main memory. This is for the purpose of to make a room in the main memory for the new process. So then, so these are the three important factors we have to keep it in our mind for managing the memory efficiently. So the key design elements for the memory management. There are certain policies used for virtual memory. So here this will give you a clear idea about, say, this is arranged in an order, how the pages are going to be moved from secondary memory to here, and how to find a space, and how to select if it needs a replacement, which particular page needs to be selected for replacement. And there are resident set process. Always you can find that those resident process will be have a reserved space in the main memory, and cleaning policy will give you details about how frequently you will able to copy back the details of process back to the secondary memory. So first is fetch policy. Fetch policy is from secondary memory to main memory. Then placement policy, how we are going to place the fetched policy from the secondary memory into main memory. Then while placing it into the second main memory, if there is no space in the main memory, then obviously we need to replace. So there we have to enforce some replacement policy to replace with the new pages. Then during the replacement we have to uh, give options for residence set management. So the operating system should not touch the residence set process. uh, like there can be a operating system associated programs and pages, so which needs to be obviously in the main memory. So those pages will not taken into the account for replacement. So here comes first fetch policy. So this fetch policy determines when a page should be brought into the main memory. There are two common alternatives are used: demand paging and pre-paging. So what is the when we can expect that, or the moment at which the processor is requesting some page, right? So if you want to execute a process immediately, the particular process which needs to be executed need to be moved from the secondary memory to the main memory. So there are two types by which we can consider for bringing the pages from the secondary memory to main memory. One is demand. Under demand, if CPU is requested for a page, some XYZ, so those page can be brought from the secondary memory to the main memory. In second case, pre-paging. Even before the CPU is requesting, we will assume it is going to be referenced soon. So by predicting those, we can bring those pages. So the difference between these two is, in demand paging, only upon finding demand, that is CPU is demanding for a particular page, and the demanded page can be brought from main memory to the secondary memory to the main memory. In the second case, pre-paging, say some page XYZ is requested, so we are not going to brought XYZ. Along with XYZ, there are some more contiguous pages are associated with it, right? So all those pages, collection of pages, will be moved from secondary memory to the main memory. So here, even there is no demand for other page, we are going to brought those pages into the main memory. So here is the explanation for what is demand and pre-paging. So demand paging only brings pages into the main memory when a reference is made to a location on the page. So if you do so, initially you can find that there are a lot of page fault, because only upon demand we are going to move pages from the secondary to main memory. So initially there were no pages, so obviously you can expect that there are many page fault. But soon after, you can find that the operating system is going to handle very nicely, so that the demanded page all will be in the main memory, so the soon after it will be settled down. In the second case, in pre-paging, it's bring more pages than needed. So as I already told you that, say if page 1 is requested, the fetching policy is going to fetch not only one, along with 1, 2, 3, 4, 5. So the bunch of all this one is demanded, but for the sake pre-paging, it is going to fetch 1, 2, 3, 4, 5. That is 2, 3, 4, 5 is not demanded, but even though that is 1 to 5, all will be fetched into this main memory, fetched from secondary memory to the main memory. So it is looks somewhat efficient, but there are some degrades. Say if you are accommodating uh, the pages whichever are not demanded, so there can be a chances that more number of replacement policies is required, because we are going to make the main memory full by keeping even not demanded pages. So we have to keep in mind that unnecessarily we shouldn't make the main memory completely full with undemanded pages. Next is placement policy. So fetch policy is nothing but it is going to fetch from secondary to main memory. Now we are in the main memory part. We have fetched. Now we have to place the fetched pages from the secondary memory into the main memory. We need to find a place where exactly this can be fit. So for this there are some policies, namely first fit, best fit, and worst fit. So let me show you by drawing a simple diagram on it. So hope it is clear to you all, visible. So let me draw a structure of main memory. So this is, assume that this is the main memory. So hope you understand that there are number of frames. The main memory is divided into a number of equal sized blocks, so we call it as a frame. And the process will be divided into number of equal sized blocks, which are called as a pages. So now the pages are coming from the secondary memory to the main memory. So let you assume now, say this is filled and this is filled with some page and these two, right? So now the yellow colored highlighted areas are free spaces, right? So now the CPUs demanded some page. So now by fetch policy we have fetched. Now we need to use a placement policy. Say these two are the blocks which are free. Now the placement policy need to decide which particular out of these two spaces, which particular block can be allotted for the incoming new page. So for this, how efficiently we can use this memory efficiently for making it fit to this block by the newly incoming pages. So for this we have three policies, namely first fit, best fit, and worst fit. So the very first one, first fit, is say it will start from looking for the free space from the beginning. So if it start looking from top to bottom, so this is the first free space. So immediately under the first fit placement policy, it will be occupied if the page is able to fit into this block. If it is not, then which will go down to find is there any place, the very first space where exactly it finds to fit those pages into the frame. It is first fit. Under best fit, it will look for, say let you assume the incoming pages of 20 KB, right? And this is of 25 KB and this is of 21 KB. So under the best fit, it will look for the exactly near about equal sized frame. So it is not going to use or allot this first block as it is 25. Even this 20 KB can exactly fit into this 21. So in best fit, this particular frame is allotted for newly incoming pages. It is called best fit. So in the under best fit, you can find that the memory is utilized efficiently. Then the last one is of worst fit. In worst fit, it is not going to look for any particular any particular order, say the pointer is here, as this is the pointer where the last placement is happened. So from this point it will look down to find the frame which can fit 20. Either it may be a 200 kb, or either it may be exactly a 50 kb or 20, whatever it comes very first, it will make it to fit. So here, even if it finds about 200 kb for 20 kilobytes of page, it will make it fit into that one. So near about 180 kb will be wasted. So we call it as a worst fit. So make a note. First one is first fit, best fit, and the last one is worst fit. Next is replacement policy. So now first we have started it with fetch policy to fetching from the secondary memory, then placement policy, how we are going to find a place in the main memory. Now there is a situation while trying to place it in the main memory, there may be no space. Say like you have a memory, and there it is completely full, so you won't find any space in it. So now it comes to a situation to replace with some page. So it is completely filled, so you need to find, say let you assume that there are 5 pages are allocated in it. So now out of this 5 you need to find which particular page can be replaced. So here the operating system needs to act very cleverly. Which particular page is not going to be soon after, or by enforcing some strategy to avoid page fault, it can select some page to replace for the new. So it can make, say it is a new page, it needs to be accommodated here by replacing the existing pages available in the main memory. So the page removed should be the page least likely to be referenced in the newer feature. It can be determined by principle of locality. Hope already we have discussed in the classroom too. So in the principle of locality, cleverly the operating system is going to be decide, it will predict whether the particular page is going to be in future, whether it is going to be used. So it can be identified by enforcing policies. So the one of the behaviors, that is past behavior. Say out of those 5 pages, it will find the frequency of, or the number of times each of this page is used. So the page whichever is used less frequently can be replaced by a new page. So likewise we do have some strategies for replacing. Now to the next one is replacement policy frame locking. So while enforcing replacement policy, we need to give importance for the pages which needs to be always in the main memory. We cannot disturb those pages. So we call it such policy as a frame locking. So why few particular frames have to be locked? This is for the purpose of, in main memory there can be a pages which belongs to kernel operating system, or there can be a control structures, there can be an IO buffers, right? So such kind of pages cannot be replaced by a user process. So those pages have to be always the same. So we call it as a residence set. So always which has to be reside in the main memory. So To make it available at all the time, we use a lock bit. So each of the frame will have a lock bit, so it can be turned to be 0 or either one. So whenever the operating system is looking for to replace any of the frame or the pages whichever resides in the particular frame, it looks for what is the status of the lock bit. If it is 0, it can be replaced. But if it operating system finds that particular frame's lock bit is 1, it is a residence set. The process belongs to a residence set, so which cannot be replaced, so which will try for in some other frames, it jumps over it, right? It won't disturb such frame bit is 1. So the basic replacement algorithms. So there are variety of replacement algorithms: optimal, least recently used, first in first out, and clock. So each of those replacement policy have its advantage. So ultimate goal of having a variety of replacement policy is that to reduce the number of page fault. So page fault is nothing but, say, as soon as a processor is requesting or trying to reference some page, if it is not available in the main memory, we call it as page fault. Say the CPU is requested for some page for the execution, but it is not available in the main memory. So immediately the operating system needs to take necessary action to find where exactly it is in the, it is obviously available in the secondary memory. So it needs to use fetch policy to fetch the referenced page from the secondary memory. Then it needs to use some placement policy, and if there were no place, then which needs to use a replacement policy. So in next video we will discuss about those basic replacement algorithms: optimal, least recently used, first in first out, and clock policies.